Hello everyone, I'm Lingbo Zhao on behalf of Yongpan Wang to give an oral presentation. The title of the paper is BinEnhance. Contents include the following 5 parts. The first part is background. Software development often reuses open source code to reduce costs. According to the reports, 96% of software uses open source code, with 89% relying on versions over 4 years. The extensive workload of code auditing and the complexity of recursive code reuses results in substantial delays in vulnerable patching. Exploiting one-day vulnerabilities in reused code has become a highly effective, low-cost, and large-scale attack method for attackers, posing severe risks. As you can see, any small mistake can cause the entire flow to collapse. Binary code research has been proven to be a powerful method for automating the detection of insecure software components. Binary code search entails the meticulous analysis of numerous binary codes to identify the most similar ones. However, as for the following figure, the syntactic structure of binary code can vary dramatically due to different compiler settings. Second part is our motivation. Based on different perspectives, we classify them into 2 categories as the following figure. Internal code semantics focus on the function itself and is derived from both the binary code embedded within the function or from its derivatives. External environment semantics focus on internal function and is inferred from other supplementary functions or indeed. In this paper, we present call dependency, date co-use, address adjacency, and string use as novel external environment semantics in our work. We illustrate our motivation with an example depicted in this figure. A and B illustrate the potential for false negative search results caused by function inlining during compilation. B and C indicates the similar internal code semantics of the handle transaction and transfer functions, resulting in false positives. E and F highlight the missing cause problem. D and E demonstrate the potential for false positive search results induced by similar function structures. We summarize the following 3 problems. First, internal code semantics of functions may exhibit substantial variations due to different compilation settings, encompassing factors like function inlining and splitting. Second, exclusive reliance on function call graphs for assistance is insufficient for addressing complex real-world scenarios. Third, current solutions exhibit limited scalability and struggle to cope with large-scale function search tasks. To solve these problems, we propose a general enhancement framework named BinEnhance for binary code search. In the node initial embedding generation stage, we encode 2 types of node, function node and string node. Function node embeddings are generated by the existing internal code semantics methods. After generating this, we use whitening transformation to reduce the dimension of node embeddings. In the function embedding enhancement stage, we design an external environment semantic graph. It contains 2 types of nodes and 4 types of edges as follows. This is our EESG construction algorithm. After constructing EESG, we propose a semantic enhancement method consisting of multi-RGCN layers and a residual block. The specific embedding conversion formula is as follows. In the similarity combination stage, we combine the semantic embedding cosine similarity and Jacob similarity of readable date features. And the combination formula and loss function is as follows. Next is the evaluation part. We select two public datasets to evaluate our BinEnhance framework. Specifically, there are two versions of dataset 2, normal and no inline, which stand for normal compilation and prohibit inlining, respectively. We select 5 existing internal code semantics model as our baselines. We would like to answer the following questions. They are: how much could be improved when BinEnhance is applied to baselines? Is BinEnhance robust against different compiler organization options and architectures? Does BinEnhance effectively elevate the impact of function inlining in binary code search? What is the contribution of each part? Does it improve the efficiency of baselines? What's the performance of BinEnhance in detecting one-day vulnerabilities in real-world firmware? We set different function port size such as 2, 16, and 10,000 in the first request. As shown in these two figures, BinEnhance demonstrates significant improvement across all the baselines, evidenced by the average increment in map scores on the two public datasets. Furthermore, its improvement for each baseline is positively correlated with the size of the function pool. We set different architectures and optimization options. As shown in these two figures, BinEnhance doubly enhances baselines across cross-architecture and cross-optimization option tasks without succumbing to significant performance dips and various compilation settings. We use two versions of dataset 2 to evaluate BinEnhance's ability to mitigate the problem of function inlining. As shown in this figure, function inlining leads to a substantial performance loss in the binary code search task, but BinEnhance mitigates the decline and improves the baseline method's ability to cope with optimization strategies such as function inlining. We carefully evaluated the effect of each part of BinEnhance. So the answer to the fourth question is each component of BinEnhance plays a crucial role in the final result. The table on the left represents the dimensions that we have transformed for each baseline using the widening transformation. The right shows the time spent by all the methods at the same settings. So the answer to the fifth question is the additional time cost of BinEnhance is in training and generating function embeddings, but it significantly reduces the time for binary code search tasks. Finally, we utilized the D3 firmware alongside the CVE vulnerability functions dataset to determine the effectiveness of the BinEnhance in enhancing real-world one-day vulnerability search capabilities. The following table is the result of all baselines and our BinEnhance. So the answer to the sixth question is BinEnhance identified 101 one-day vulnerabilities in 37 firmware images with 67.9% map scores, which is 12 more vulnerabilities detected than HermesSim and a map score of 7.7% higher. So our conclusion is we propose a binary code search enhancement framework BinEnhance, which enhances internal code semantic models with valuable external environment semantic information, thereby reducing the false positive and false negative. That's the end of my presentation. Thank you.